Imagine a man who spent 40 years staring at the sky from the rooftops of a small city on the banks of the Euphrates River, not because someone paid him handsomely to do it, not because a king commanded it, but because he could not stop. He was driven by a question that had eaten at him since childhood. Why did the old Greek master's numbers not match the sky he actually saw? He lived in the 9th century. He had no telescope, he had no computer. He had only handcrafted instruments, a river breeze, and a mind that refused to accept inherited error. And yet, by the time he died, he had produced measurements of the solar year so precise that European astronomers would still be copying his tables 600 years later. Copernicus would cite him by name. Tycho Brahe would call his work foundational. Galileo would lean on his calculations. But here is the mystery that this story must answer. Who made him? What turned a boy born into a family of stargazers on the edge of the ancient Silk Road into the most rigorous observational astronomer of the medieval world? And what does the answer tell us about how any great mind is truly formed? Stay with this story to the end, because the most important thing about Al-Battani is not what he discovered. It is why he could not rest until he did. Welcome to Numbers and Narratives by Blesswright, where we go beyond the equations and the dates to ask the questions that history books almost always skip. Today's story is about a man known to medieval Europe as Al-Battani, a name that whispered through the corridors of Bologna and Oxford for centuries. His full name was Abu Abdallah Muhammad ibn Jabir ibn Sinan al-Raqi al-Harrani al-Sabi al-Battani. He was born around 858 CE in the ancient city of Harran, in what is today southeastern Turkey, near the Syrian border, and he would go on to reshape how humanity understood the heavens. If you are new to this channel, please subscribe and hit the notification bell. We release deep dive documentary scripts on the greatest mathematical and scientific minds in history, and we never tell the story the way your textbook did. And if you have been here before, you already know what is coming. We are going to go somewhere the history books rarely go. We are going to go back before the discoveries, back to the soil in which this genius grew. By the end of this documentary, you will understand something that most people who have heard Al-Battani's name do not know. That his greatest scientific achievement was not a measurement or a formula, it was a habit of mind. And that habit was built, brick by brick, in a city that the ancient world considered the last outpost of a vanishing cosmos. To understand Al-Battani, you have to understand Harran. Not the Harran of tourist maps or ancient ruins, but the living, breathing Harran of the 9th century. A city that carried within its walls one of the most unusual spiritual and intellectual traditions in the entire medieval world. Harran sat at a crossroads, literally and figuratively. It was a trading city on the northern fringe of the Fertile Crescent, close enough to Byzantium to feel its cultural breath, close enough to Persia to have absorbed centuries of its astronomical legacy, and by Al-Battani's time, firmly within the orbit of the Abbasid Caliphate, whose capital in Baghdad was, at that very moment, the most intellectually alive city on earth. Caravans from the east and the west passed through Harran. Merchants, scholars, physicians, and philosophers all moved through its dusty streets. Ideas traveled with goods along the Silk Road, and Harran was a place where those ideas pooled and settled. But what made Harran truly singular was its indigenous religious community, the Sabians. Al-Battani's family was Sabian, a fact declared in his very name, with the word al-Sabi marking his lineage and his community. The Sabians of Harran were a group whose belief system was ancient and deeply intertwined with the celestial bodies. They were not Muslim, not Christian, not Jewish in the conventional sense, though they had borrowed threads from all three traditions. What bound them together, what animated their rituals and their theology, was the sky. The sun, the moon, the planets, the fixed stars. These were not merely physical phenomena to the Sabians of Harran. They were living presences, divine intermediaries, objects of veneration and careful study. To be born a Sabian in Harran in the 9th century was to be born into a home where the sky mattered in the most immediate and personal way. Prayers were oriented toward the celestial bodies. Festivals followed planetary cycles. The intellectual life of the community was inseparable from the study of the heavens. This was not superstition dressed up as science, nor science dressed up as superstition. It was something older than both, a tradition of sky watching that had been practiced in Harran for more than 1,000 years before Muhammad ibn Jabir was born. His father was Jabir ibn Sinan al-Harrani, and here is where the story of formation begins in earnest. Jabir was not simply a man who looked at stars. He was an instrument maker. According to the 10th century bibliographer Ibn al-Nadim's Fihrist, one of the most important catalogs of medieval Islamic intellectual life, Jabir was known for constructing astronomical instruments, the precise mechanical tools that were essential for observational work. Astrolabes, armillary spheres, sundials, and graduated rings. In an era before mass manufacturing, these instruments were handcrafted objects of extraordinary precision, requiring not only technical skill but a deep theoretical understanding of geometry and celestial mechanics. The craftsman who built an astrolabe had to understand what the astrolabe was supposed to represent: the projection of the celestial sphere onto a flat plane. You could not make one well without thinking geometrically about the cosmos. This means that the boy who would become Al-Battani grew up in a workshop. He grew up watching his father's hands move across brass and copper. He grew up hearing the language of circles and angles and celestial coordinates spoken not in a classroom but in the heat of a craftsman's labor. The precision that would later define his astronomical work, the refusal to accept rounded numbers, the insistence on measurement over inheritance, was not learned from a book. It was absorbed through watching a man who built the very instruments of precision with his own hands, and who knew that a poorly calibrated astrolabe would mislead every astronomer who used it. Jabir taught his son through craft rather than lecture that accuracy was not pedantry. It was respect. Respect for the sky, respect for the user of your instrument, and respect for the truth. We do not know the name of Al-Battani's mother. History, as it so often does with women of the medieval world, has swallowed her identity into silence. But we can reason about her world. She was a Sabian woman in 9th century Harran, which means she raised her children inside a community that valued both faith and learning. A community that was small enough to feel embattled by the surrounding world, but ancient enough to feel a fierce pride in what it knew. The Sabians of Harran were surrounded by the 3 Abrahamic faiths, each of which had at various points questioned their right to exist. But under the Abbasid Caliphate, the Sabians had found a degree of tolerance and even respect, partly because the Caliph's scholars recognized that Harran's intellectual tradition, its astronomy, its mathematics, its Neoplatonic philosophy, was genuinely valuable. The mother who raised Al-Battani raised him, in all probability, with a simultaneous awareness of cultural vulnerability and intellectual pride, the sense that his community carried something precious, and that he had a duty not to let it die. The economic condition of the family was, by medieval standards, stable. Instrument making for the Abbasid court and its scholars was a skilled trade with real prestige. The family was not aristocratic, but they were not struggling. This matters because it gave the young Muhammad ibn Jabir something that poverty rarely permits: time. Time to read, time to observe, time to think slowly without the immediate pressure of survival. He was not a child laboring in fields at dawn. He was a child in a workshop where thinking was the work. The educational environment of 9th century Harran was shaped by 2 forces simultaneously. One was the local Sabian tradition of astronomical and philosophical teaching, which had deep roots reaching back through the Hellenistic world to the Babylonian astronomers who had worked in the region centuries before. The Sabians had preserved and transmitted Greek astronomical texts with a devotion that was almost liturgical. To know Ptolemy's Almagest was, in some sense, to honor their cosmological faith. The other force was the extraordinary intellectual revolution unfolding in Baghdad, just over a week's journey to the south and east along the Euphrates. The Abbasid Caliph Al-Ma'mun, who reigned from 813 to 833 CE, in the generation just before Al-Battani's birth, had established and richly funded the Beit al-Hikmah, the House of Wisdom, where scholars from across the known world were translating Greek, Persian, and Indian scientific texts into Arabic and then pushing beyond them. This was not mere translation, it was transformation. And the energy of that transformation radiated outward from Baghdad like heat from a furnace. Al-Battani grew up reading Arabic translations of Ptolemy, Euclid, and the Indian astronomical tradition. He grew up in a moment when the greatest minds in the Islamic world were not simply copying the Greeks. They were correcting them. Al-Khwarizmi had already laid the foundations of algebra. Al-Kindi was writing on optics. And a new generation of astronomers was looking at the sky with fresh eyes and finding repeatedly that Ptolemy's Almagest, the Greek masterwork that had dominated astronomy for 7 centuries, contained errors, accumulated errors. Small discrepancies between its predictions and actual observation that had been tolerated for generations, but were now, in the light of the Abbasid measurement program, becoming impossible to ignore. For the young Al-Battani, reading Ptolemy was not an act of reverence, it was an act of suspicion. His father had taught him that an instrument with a small flaw would produce large errors over time. And here was the greatest astronomical instrument ever constructed, the mathematical framework of the Almagest, and it was producing errors. Not enormous errors, but consistent ones. The kind that drove a precise mind mad, the kind that demanded correction. We do not have detailed records of Al-Battani's specific mentors or teachers in the way we have records for some other scholars of the period. What we know is that by the time he was a young man, he had settled or relocated to Raqqa, the city on the Euphrates about 3 days' journey to the south of Harran in what is today northern Syria. Raqqa was at that time a significant city, a former Abbasid provincial capital, with resources and a scholarly community sufficient to support serious astronomical work. It was here, in Raqqa, that Al-Battani would spend most of his working life, building his observatory, crafting and calibrating his instruments, and beginning the decades-long program of observation that would become his life's work. He had a son whose name appears in later records as a minor historical figure, which suggests a domestic life, a family, a household, the rhythms of ordinary existence woven through the extraordinary intensity of his research. The image of Al-Battani that emerges from the sources is not of a monastic scholar sealed away from the world, but of a man embedded in a community, with civic responsibilities and personal relationships who nevertheless managed to maintain for 40 years the kind of rigorous nightly discipline that most people cannot sustain for 40 days. That discipline, that combination of human ordinariness and scientific obsession, is itself one of the most remarkable things about him. The awakening of Al-Battani's genius did not come in a single flash. It came the way most genuine scientific breakthroughs come, slowly, through accumulation, through the piling up of small discrepancies that eventually become impossible to dismiss. He began his systematic observations around 877 CE when he was approximately 19 years old. Though some scholars place the beginning of his recorded observational program a few years later, around 880 CE, what is clear is that he started early and he started methodically. His approach from the beginning was not to theorize first and observe second, as some astronomers of his era did. He observed first. He measured everything he could measure. He wrote down every result, and then, only then, did he sit with the numbers and ask what they were telling him. One of the first things they told him was that Ptolemy was wrong about the length of the solar year. This sounds like a small thing. It is not a small thing. The length of the solar year is foundational. Every calendar, every prediction of a solstice or equinox, every calculation of where a planet would be on a given night, all of it rested on an accurate measure of how long it took the Earth to complete one orbit around the Sun, or in the geocentric model that Al-Battani still used, how long the Sun took to return to the same position in its annual cycle against the fixed stars. Ptolemy had placed the tropical year, the time from one vernal equinox to the next, at 365 days, 5 hours, 55 minutes, and 12 seconds. This was, for the 2nd century CE, a genuinely impressive measurement. But by the late 9th century, 7 centuries of accumulated error had made the discrepancy visible to anyone with good instruments and the patience to use them carefully. Al-Battani measured the tropical year at 365 days, 5 hours, 46 minutes, and 24 seconds. The modern rigorously confirmed value is 365 days, 5 hours, 48 minutes, and 45 seconds. Al-Battani was off by less than 3 minutes. Ptolemy had been off by nearly 10. Using instruments made of brass and copper, with no optics, in the 9th century, Al-Battani produced a measurement of the length of the year that was within 3 minutes of the truth. But how? This is the question that most histories skip over. How does a man standing on the roof of a building in Raqqa with a graduated brass ring measure the length of the year to 3-minute accuracy? The answer is not talent. The answer is discipline multiplied by time. Al-Battani did not measure a single equinox and announce a result. He measured equinoxes and solstices repeatedly, over years, cross-checking his results, calibrating his instruments against each measurement, building a statistical sample that reduced random error the way only sustained patience can. His father had taught him this without ever using the word statistics. An instrument maker knows that a single measurement is a guess. 100 measurements, carefully averaged, begin to approach the truth. The obsession that had been kindled by reading Ptolemy, the small, sharp awareness that the numbers did not match the sky, had found its object. Al-Battani had identified his life's problem, not a single question to answer, but a whole architecture of inherited knowledge to verify, correct, and in some cases rebuild. The Almagest had stood unchallenged for 7 centuries. He was going to check every claim in it that he could check, not out of arrogance. Out of the craftsman's instinct his father had planted in him, that inherited work, however brilliant, must be tested before it is trusted. The work that Al-Battani produced over his 40-plus years of observation in Raqqa was gathered into a single monumental text known as Zij, the Kitab az-Zij, or Book of Astronomical Tables. The Arabic word Z refers to a specific genre, a systematic compilation of astronomical tables, observations, and theoretical explanations designed to allow anyone who knew how to use them to predict the positions of the sun, moon, and planets, calculate eclipses, and determine the dates of religious festivals and astrological events. Al-Battani's Zij was the most carefully observed and mathematically sophisticated astronomical handbook produced in the Islamic world up to that point. It contained 57 chapters and a dense collection of numerical tables representing the fruit of decades of measurement. It was translated into Latin in the 12th century under the title De Motu Stellarum, on the motion of the stars, and it remained one of the foundational texts of European astronomy until well into the 16th century. But we must go deeper than the title and the genre. We must sit inside the specific discoveries and understand what they required of the mind that made them. Begin with trigonometry, because this is where Al-Battani's contribution is most technically profound and most consistently misunderstood. When Ptolemy constructed the mathematical framework of the Almagest, he did so using a tool called the chord function. In ancient Greek astronomy and mathematics, angles were related to the lengths of chords, straight lines cutting across circles. The chord function was workable but cumbersome, requiring tables of enormous size and producing calculations that were laborious to perform. The Indian mathematical tradition, whose texts had been translated into Arabic in the decades before Al-Battani's birth, had introduced a superior tool, the sine function, which related an angle directly to the ratio of the opposite side of a right triangle to the hypotenuse. The sine was more natural, more compact, and ultimately more powerful. Al-Battani adopted the sine function and made it the heart of his astronomical calculations. But he did more than adopt it, he extended it. He was among the first mathematicians to use what we now call the tangent and cotangent functions with explicit awareness of their properties and their application to spherical trigonometry, the branch of mathematics that deals with triangles drawn on the surface of a sphere, which is precisely what you need when you are calculating positions on the celestial sphere. He developed systematic methods for calculating the altitude of the sun and the time of day using the cotangent, and he produced tables of these functions to a degree of precision that made practical calculation far more accurate than anything available in the Greek tradition. Why was he able to do this when others had not? Because his father's workshop had given him something that purely theoretical mathematicians lacked: the understanding that mathematical tools exist to serve measurement. He did not adopt the sine function because it was mathematically elegant, though it was. He adopted it because it made his calculations more accurate and more manageable. He extended it into tangent and cotangent because those were the functions his specific observational problems required. He was not doing mathematics for its own sake. He was doing mathematics the way his father made instruments, to solve a real problem, and to solve it precisely. His discovery about the solar apogee is perhaps his most sophisticated astronomical achievement, and it is the one that most directly reveals the depth of his engagement with Ptolemy. In Ptolemy's model of the solar system, the point at which the sun was farthest from the Earth in its annual cycle, the solar apogee, was fixed. It did not move. Ptolemy had placed it at a specific position in the zodiac, and his model assumed it stayed there forever. Al-Battani's decades of careful observation showed that it had moved. Compared to Ptolemy's value, the solar apogee had shifted by approximately 16 to 17 degrees. Al-Battani correctly concluded that the apogee was not fixed but was slowly moving through the zodiac, completing a full circuit over an enormously long timescale. He did not have the heliocentric model that would have explained why. That was still 7 centuries away, waiting for Copernicus, and even Copernicus would not fully explain the phenomenon. But Al-Battani understood that the data demanded a correction. He could not explain the physics. He could document the fact. And in doing so, he pointed to one of the genuine inadequacies of the Ptolemaic system, an inadequacy that would eventually crack it open entirely. His measurement of the obliquity of the ecliptic, the tilt of the Earth's axis relative to its orbital plane, or in geocentric terms, the angle between the ecliptic and the celestial equator, came out to 23 degrees and 35 minutes. The modern value for his era is approximately 23 degrees and 35 minutes. He was essentially exact. This was not luck. Measuring the obliquity requires careful observation of the sun's maximum altitude at the summer solstice and minimum altitude at the winter solstice, corrected for atmospheric refraction, the bending of light as it passes through the Earth's atmosphere, which makes objects near the horizon appear slightly higher than they actually are. Al-Battani understood this correction and applied it. Most of his predecessors, including Ptolemy, had either ignored it or underestimated it. He was also the first astronomer in history to observe and record the possibility of annular solar eclipses. Eclipses in which the moon, being at the far end of its elliptical orbit and therefore appearing slightly smaller than usual, does not fully cover the solar disk, leaving a ring of sunlight visible around its edge. Ptolemy had not described this phenomenon. Al-Battani observed it, recognized that the apparent size of the moon varies, and correctly inferred that this variation meant total solar eclipses were not always total. A subtle but genuinely important insight into the geometry of the Earth-Moon-Sun system. A man who spends 40 years measuring the sky on rooftops in the Mesopotamian night pays a price that no table of astronomical data can record. The Sabian community of Harran, to which Al-Battani's family belonged, was under sustained pressure throughout his lifetime. The Abbasid Caliphate's relationship with non-Muslim minorities was complex and fluctuating. Under certain caliphs, the policy was one of genuine tolerance. The Sabians were recognized as a protected religious community. The al-Dima and their scholars were valued for their astronomical and philosophical knowledge. But the political winds shifted with every new caliph, and the 9th century was a period of considerable internal turbulence in the Abbasid world. Al-Battani lived through the reigns of multiple caliphs, through political crises, through the gradual fragmentation of centralized Abbasid authority into a patchwork of regional powers. The world he was born into was not the world he died in. He converted to Islam at some point in his life, or was recorded as a Muslim in later sources, though the historical picture is complicated, and some scholars believe his family's Sabian identity remained culturally significant even as they formally adopted Islamic practice. The tension between inherited identity and the religious culture of the dominant civilization is something that history tends to smooth over with a few sentences. But for the man living inside that tension, it was real and daily. He was, in a deep sense, a bridge figure. Born into a tradition that had venerated the sky for 1,000 years, working within a civilization that had transformed star study into rigorous mathematical science and writing for posterity in a language, Arabic, that was not his community's ancient tongue. His later years brought a journey that underscores the political and personal vulnerability of scholars in the medieval world. Historical records indicate that near the end of his life, Al-Battani traveled from Raqqa to Baghdad to present a petition, or to advocate on behalf of the people of Raqqa in some civic or administrative dispute. He died on the return journey in 929 CE at a place called Qasr al-Jis, near the city of Samarra in modern-day Iraq. He was approximately 70 years old. He died on the road, away from his instruments, away from his observatory, on an errand that had nothing to do with the sky. There is something quietly devastating about that detail. A man who had spent the better part of a lifetime measuring the motion of the sun died in the middle of a journey that the sun had long since plotted its indifferent course above. His instruments in Raqqa, the armillary sphere, the mural quadrant, the graduated rings that he had calibrated and recalibrated through thousands of nights, would have stood silent, waiting for an observer who would not return. And beyond the physical circumstances of his death, there is the larger loneliness of his intellectual project. Al-Battani worked at the frontier of what was knowable with the tools he had. He pushed those tools to their absolute limit. He knew, because he was precise enough to know, the exact boundaries of his own uncertainty. The places where the measurements were ambiguous, where the instruments had limits he could not overcome, where the theoretical framework he had inherited from Ptolemy was straining under the weight of evidence that it could not fully accommodate. He lived with the discomfort of partial knowledge. He corrected what he could. He documented what he could not yet explain. The isolation of that position, of being the person in the room who sees the problem most clearly and has the fewest tools to solve it, is a particular kind of loneliness that belongs to those who work at the edge of human knowledge. Al-Battani spent 40 years at that edge. He did not have colleagues who fully shared his level of rigor. He did not have successors, in his own time and place, who would immediately build on his work. His ZG would travel west, translated into Latin, and be absorbed by astronomers who came centuries after him in a civilization he never knew. The community that would most fully benefit from his work could not thank him. He gave his best to a future he would never meet. Here is what history misunderstands about Al-Battani, and through him about the entire class of scientists we call the Great Ones. We tend to explain genius by pointing to its outputs, the measurement, the formula, the discovery. We say that Al-Battani was great because he measured the year with extraordinary precision, because he introduced the sine function into Western astronomy, because he discovered the motion of the solar apogee, and all of that is true. But when we explain genius by its outputs, we are doing something intellectually dishonest. We are confusing the result of a way of thinking with the way of thinking itself. We are pointing at the fruit and pretending we have described the root. The root of Al-Battani's genius was not intelligence. It was a very specific relationship with inherited knowledge, a relationship he learned not in a classroom but in his father's workshop, watching a man build instruments that had to be right, not approximately right, not within an acceptable margin, but right. Because an astrolabe that is slightly wrong will send the astronomer slightly wrong. And slightly wrong, compounded over time, becomes catastrophically wrong. This is the craft ethic as an epistemology. It is the understanding, absorbed through work rather than argument, that truth is not a possession to be inherited. It is a standard to be met. Every generation that inherits knowledge without testing it is not preserving that knowledge. It is eroding it. The inherited measurement drifts from the sky it was supposed to describe, and the longer you wait to notice, the farther you drift. What Jabir ibn Sina transmitted to his son Muhammad was not a body of knowledge. It was a relationship to knowledge. The discipline to measure again what has already been measured. The courage to say that the great Ptolemy was wrong, not out of arrogance, but out of the craftsman's refusal to use a flawed instrument. The patience to accumulate not one measurement, but hundreds, because one is a guess, and hundreds begin to tell you something real. And here is the part that the history books skip entirely. This relationship to knowledge was not born in a vacuum. It was the product of a community, the Sabians of Harran, who had staked their spiritual identity on the accuracy of their skywatching. For a Sabian, the difference between where the planet was supposed to be and where it actually was in the sky was not merely a scientific question. It was a question of faith, of ritual coherence, of the integrity of a way of life. You could not pray to the sky and then misread the sky. The imperative to be exact was, for the Sabians, older than science. It was older than mathematics, it was devotional. Al-Battani was formed by the intersection of two worlds that history usually keeps separate. One world said, measure precisely because precision is craft. The other world said, measure precisely because precision is prayer. Both of those imperatives, carried in his blood and his upbringing, collided in the observatory at Raqqa and produced something that neither tradition could have produced alone. 40 years of systematic, relentless, disciplined observation that advanced the science of the heavens by centuries. This is what history misunderstands. It was not his brilliance that made him different. It was his compulsion. And his compulsion was not pathological. It was devotional. He measured the sky the way a craftsman finishes a surface, not because anyone demanded it, not even entirely because his intellect required it, but because the sky demanded honesty. And somewhere, deep in the formation of his character, he had decided that honesty to the sky was a kind of sacred obligation. Copernicus cited him. Tycho Brahe used his measurements. Galileo built on his work. None of them knew a Sabian craftsman's son from Harran had given them their foundation. But the foundation held. It held because it was built the way his father taught him to build. Not to be impressive, but to be right. There is a crater on the moon named Al-Battani. It is a large ancient formation, nearly 130 kilometers across, with walls worn smooth by billions of years of meteorite impacts. When you look at the moon on a clear night, you are looking at a feature that bears the name of a man who spent his life looking back. What can we take from this story, not as a historical curiosity, but as something that actually matters to the way we live and think today? Al-Battani lived in a world of inherited knowledge. The Almagest had stood for 7 centuries. It was in every practical sense the authority on the cosmos. To question it was not merely intellectually difficult. It was culturally strange, the kind of thing that invited dismissal, even ridicule. The safe path was to accept, transmit, and honor what the great Ptolemy had established. Most people took that path. Most people always take that path. Al-Battani could not take it, not because he was rebellious or arrogant, but because a craftsman's son could not look at a measurement that did not match reality and call it good enough. His formation would not permit it. The values instilled in him before he ever opened a book, values that said precision is not obsession, it is respect, that inheritance must be tested before it is trusted, that the world you actually observe matters more than the world you have been told to expect. Those values made the safe path impossible for him. Think about the domain in your own life where you have accepted inherited knowledge without testing it. Think about the frameworks, professional, personal, philosophical, that you received from others and have simply assumed to be accurate because they have the weight of authority behind them. Al-Battani spent 40 years asking, does the sky actually match what the book says? What equivalent question are you not asking? What measurements are you not taking? Great minds are not formed by talent alone. They are formed by the intersection of inherited values, cultural pressure, personal discipline, and a specific kind of problem that fits the exact shape of the mind that has been built to encounter. Al-Battani's problem, the gap between Ptolemy's numbers and the actual sky, was waiting for him the way a key waits for the lock it was made for. But the key had to be shaped first. It took a Sabian community, a craftsman father, a childhood in a workshop, a civilization in the middle of its most creative century, and 40 years of cold nights on the banks of the Euphrates to shape it. That is how genius is made. Not in a flash, not by accident, but by the slow accumulating pressure of a world that asks everything of a specific kind of mind. If this story moved you, if it changed how you think about how knowledge is formed and how great minds develop, please like this video and share it with someone who is asking hard questions about the world they have inherited. Subscribe to Numbers and Narratives by Blesswright if you want more documentaries like this, stories from the history of mathematics and science that go beneath the surface, that treat ideas as human, things built by human beings with human histories. The next time you look up at the night sky, remember that someone 12 centuries ago looked up at that same sky from a rooftop in Raqqa and refused to let an error stand. He did not have a telescope. He did not have a computer. He had a craft ethic, a devotional discipline, and a mind formed in the exact right way to do exactly what needed to be done. His name was Al-Battani, and the sky still holds his numbers.